All right, we are back, and this time I want to talk to you about Catalyst EVPN on iOS XE 17.3. It's kind of got a ring to it. iOS XE 17.3, you know me, package for free. Hey, this is why I'm not in the rap industry. Anyway, okay, so Catalyst EVPN, Ethernet Virtual Private Network. Why I want to talk to you about this is because it's interesting, and I've been working with it, and I love to share. So we have an agenda. I'm not going to fill this into one video. It would be long and it wouldn't be fair, and I would dictate it. So we are going to split it over a few. Today we'll talk about what it is and why do I care. I think they're often the most important parts to discover. And give me some theory. I'll have a bit of theory. Why is it doing it this way, and what's the wonderful things that can do, and then later on we'll talk about these other elements that you can dog. I don't know why there's a dog in there. We'll talk about underlay multicast, tenant root multicast, overlay gateways, and some external connectivity. But I'll do that later in the series. This is our lab. Should we need it? We'll revisit that when required. It's ready to go. I don't think we'll need it today, but we'll see. Read the docs. I say read the docs. If you're interested, type that into Google, click the first link, have a read through, and you'll see everything that I'm talking to you about. Free to look at and enjoy at your leisure. But if you want to hear me talk to you while I slowly, gently send you to sleep, whenever you happen to be watching this, then you're in for a ride. Or not, you can't ride. So why do we care? Ultimately, this is why, because you want to turn your protocol stack and your network from this to this. Holy crikey, that's good. Can I really do that? You probably can really do that, but with caveats. Depending on your requirements and what you need, then it may grow out. But fundamentally, this is true. So what is EVPN? It's kind of the question I should have asked first. It's a little bit like MPLS VPN or MPLS VPLS as well, where we have an overlay, but this time the overlay is built on VX-LAN, so you can see VX-LAN there, and not on labels like we have with MPLS. And we can build both the layer 2, the VPLS type overlays, as well as layer 3, like the MPLS VPN type overlays as well. And we can do both integrate route and bridging, so we can have both layer 2 and layer 3 within the same fabric. Why? Why would one choose EVPN over MPLS? Very good question, very good question. Less is more. Would you rather run this protocol stack, as I've shown before you, VX-LAN and BGP, or would you rather run the MPLS and LDP and the other elements that go along with such a deployment? With EVPN, so we can reduce that 15 or so down to 2 to 7. I say 2 to 7 because, realistically, it's going to look a little bit more like this. If we have just a fabric, an EVPN fabric, we could get away with just BGP and VX-LAN, but you're going to have to connect to the outside network, for your tenants particularly, because we build networks to services, and we need to connect to them. So maybe there's a layer 2 service, so we need a spanning tree. Maybe you connect to a partner network and it's running OSPF, so you connect in a typical kind of PEC type setup in that way with OSPF. You need multicast, it's PIM, and so on and so forth. But your requirements and your use cases will drive what your protocol stack is. I mentioned a fabric. What is a fabric? You've probably heard this term thrown around almost as much as the term next generation. Next generation. I think we're at next by now or something. Anyway, what does it mean? The word fabric is a piece of cloth, right? It's on my jumper. I should like my DevNet jumper. I said this in the post for doing my DevNet. I don't know which one it was. The DevNet. A CCNA equivalent entry exam. You should do it. It's a good exam. But the fabric, yes, piece of cloth. It's kind of overlaid on top of my skin. Where in this analogy, the cloth is the VX-LAN overlay, and the skin is the underlying IP network underneath. So, fabric is an overlay on top of an underlay. That's how I would kind of see it. We have others. We have other beasts. We have SDA and we have ACI. But in those two particular examples, they are quite They are quite prescriptive in nature and more of a software-defined network, an SDN, and that the controller derives what the configuration set would be pushed down to the nodes. EVPN, it's more UDN, if you like, user-defined networking, where there is no controller. You define what your fabric will look like, and it's totally customizable. You can do with it as you please, caveat, provided it's supported. But it's not as prescriptive as the other two. Let's talk a little bit about roles. I'm going to move myself up here. Boom. Okay, so we have different types of device roles. Of course, there's a border, there's a spine, there's a leaf, and there's an intermediate node. What are they? So a border is essentially it's your gateway to the external networks. Eventually, you have to connect to somebody else. If you're connecting to the service provider by an EVPN peering, that'll be via a border. You're connected to another small network, which is running some other protocols, say OSPF, for example, or ISIS. You would connect to them via a border. For your spines, they're basically your BGP route reflectors. They're going to be advertising your layer 2 and your layer 3 routes throughout the fabric. Typically, in a leaf spine architecture, they're the central point in your network where all your leaves and your other nodes connect to. Which brings me on to the leaf. The leaf essentially connects to endpoints or the tenants, and they are your VTEX, your virtual tunnel endpoint destinations. So when a packet is encapsulated within the EVPN fabric, and the tunnel is created, essentially it's tunneled across the network, the destination are the leaves. An intermediate node, well, he's just a mere packet switching beast. He doesn't even have to be a catalyst, he can be whatever you like, as long as he supports IP in, IPL, and let's say Jumbo MTU. VX-LAN adds that extra 50 bytes overhead for encapsulation. So if you tick those boxes, then, put in whatever you like there. And then there's support. So we're talking about Catalyst here. So it's a Catalyst-based EVPN. It is around on the Nexus already in the data center world, and I think we have DCNM that can deploy this in a few clicks, nice and simple. So do not be confused. We're focusing on the campus and Catalyst here. And we have these nodes. We have the Cat 9Ks, the 93, 94, 9500s. They can be leaves or spines. And the 9500 high performance models or the 9600s, they can do 4 roles. They are mini gods. We thank them. And then we have the 9200s, which are not supported, unfortunately. You can't buy a cheap switch and expect it to solve all of your world's problems now, can you? Buy something decent. Super key important point. These roles are not fixed. No, young buckies. They are. You could have a border leaf. You could have a border leaf spine. You can mix and match. There is no limit here apart from the platform support. At the network I just recently deployed with EVPN, everything was a spine leaf architecture. In particular, they were all running IBGP full mesh between them, so they were all spines, no need for a route reflector. They all connected to tenants, to endpoints, so they're all leaves, and in some cases where we had external connectivity, we did an eBGP handoff, so they were borders as well, so we had a mix of border leaf spines and leaf spines everywhere. So that brings me back to the UDN. It's the user-defined networking. It's pretty customizable. What is it and why do I care? What's the title of this slide? So this leads me on to the promise. In the presentation, there's this thing called the promise, which is where I tell you what you're going to get from this if you continue to listen. But let me tell you what's good about this. With EVPN, you get this optimal end-to-end transport. Great, that sounds like woolly marketing. What does that mean? Well, if you need layer 2 end-to-end, same subnet everywhere, what do we have? We have spanning tree. It's been around for a long time. It's good, it does its job very well, but it has nuances, right? We have to block links, we have to run loop prevention mechanisms and all the trouble that go with spanning tree. And we have to run spanning tree, right? If I look at this slide here I've shown you, we've said that we can actually remove spanning tree instead of VX-LAN and BGP. So how do we do this? Well, We use, I'll get to how we do this, I'm jumping ahead, but essentially we'll explain how we can achieve this via EVPN. The main point I'm trying to drive here with optimal end-to-end transport is the infrastructure is all layer 3, it's rooted, and it uses the known methods we have for layer 3, resilience, redundancy, and troubleshooting to work, which is great. Endpoint discovery, so we get optimal endpoint discovery as well. So what I'm talking about here is ARP. I don't know why I said it like that. But with ARP in the spanning tree topology, we know that we do this flood and learn type behavior. If we don't know where a particular MAC is, we'll flood it everywhere. Then if we moved on from spanning tree and we looked at a VX-LAN, so I'm not talking EVPN, I'm talking VX-LAN architecture, that also uses flood and learn to do endpoint discovery. Now we augment this with EVPN and then we eliminate flood and learn. How do we do this? Well, let me tell you. When a client first connects and talks to the network, be it via DHCP, be it via sending out a GARP or some sort of packet, the leaf that it's connected to, he learns the IP and the MAC address. And then he takes that IP and MAC address and he turns that into a BGP update and sends that to all of the other leaves. Well, actually to the spines. Well, it's the leaves. Since to the BGP pairs, let's call it that, depending on your BGP architecture, whether you have a root reflector, full mesh, whatever, how you got BGP. Go look up BGP. Then, so a remote leaf, a client comes on and he says, hey, I need to figure out where my buddy is, and he sends out an ARP request. That ARP request arrives on his local leaf, and the local leaf goes, oh, well, I have this information in my BGP table. It was sent to me via the remote leaf that's connected to this endpoint, and I can go ahead and unicast this ARP directly to the remote leaf where the endpoint is versus to all leaves. So we get this optimal endpoint discovery, which is great. But as with everything, there are nuances and use cases where this doesn't apply. What if the endpoint you were trying to discover had never sent a packet in his life? What if he never does? What if he's silent until spoken to? He's a very, very, very polite client. Doesn't speak unless spoken to. I don't know if that's polite. It's something you tell children. That's just could be a little odd. But in this case, when we send out a ARP request and the ingress leaf doesn't have that information in its BGP table, he will flood that to all of the leaves, in particular the VTEPs that are part of that VX-LAN segment. So it is flood and learn fallback behavior if the information is not already prevalent in the database. All right, 2 more points and I'll move on to the next few slides. Scalable, it is scalable. How is it scalable? It can explode to, how many is it? I wrote down 16 million tenants, 16 million. Well, that's a lot. With VLANs, we have the limit of 4,094 VLANs, where with VX-LAN, we have a larger block, so we can scale to 16 million. Any network I've worked on, I've never deployed anything near that scale, so I'd be interested to know if you have, because that's quite a lot. Anyway, and it's simple and repeatable. That seems to be true, because we can build a simple 2-tiered topology. We can have an underlay IP transport, that could be BGP if you like, and then an overlay control plane, which is also using BGP, but the EVPN address family. I haven't built one just pure BGP and VX-LAN myself. The last fabric like this I built did compromise or consist of all of the protocols laid out here. It was VX-LAN. In fact, the underlay was OSPF. Then we built our BGP, EVPN on top. We had spanning tree. Why do we have spanning tree? Because we connected to downstream switches on trunk ports, so we had to run spanning tree towards those endpoints. And then we had PIM and IGMP because we were supporting multicast. And then, so the stack was virtual or cover off, but it's going crazy. I don't know how long it's been like that for. Sorry, so we can't layer to dual home in EVPN, what I mean here is we can't have an access switch which is connected to two EVPN leaves, because we'll end up with a loop. And how we solve this, if you need to do layer 2 dual forming or dual homing, you can stackwise virtual those leaves, or resolve it with another method. Use your imagination. So enough of the kind of preamble here. Let's dive into theory. I've got 2 slides on theory, and they focus on VXLAN and then on BGP. And then we're kind of done with this talk, and the next one will be more about the configuration elements and kind of maybe some packet walks, because they're really interesting. So we have VX-LAN for encapsulation. What can I say about VX-LAN? This is what it looks like. We've got our original layer 2 frame from the client. We have our VX-LAN header, which is sent UDP, and then a new IP header, which is the destination leaf. So it's the VTEP IP, and then of course hop by hop we add a new MAC. But let's have a look. Let's have a look at this in a bit more detail. I want to move my picture. Can I get to that guy over there? Let me move my mic. I'll move him out of the way. So look at me for a minute. All right. So what we have here is we've got a new outer source and destination. So this is an IP header. This is the VTEP, the endpoint. This is the address of the leaf. So the source leaf, destination leaf. Then we have let's call it the passenger protocol, if you like, if we're talking about GRE. But this is the tenant data. It's the original layer 2 frame. Layer 2, right? So we're carrying the layer 2 as well as the layer 3 information here. All right. Moving on, in the source port. So the source port, interestingly, this is defined in the RFC as being a hash of the inner frame's headers. And why we need this? For load balancing. Why is this super important? Guys, it's super important because, let me move myself up there. It's super important because if we were to use the same source destination port, we would just polarize the same links. You know, if the packet's traversing the core, we do a hash on the UDP source destination port and the outer destination IPs, and it's just going to go across the same link and polarize that link. By doing a hash, we get a bit more entropy, and then we can make use of our underlying IP infrastructure. And then we've got the VNID, the virtual network identifier, which identifies the VRF or the VLAN that the packet's coming from. So to give an example here, we have a client connected to leaf 1 and a client connected to leaf 2. Client in leaf 1 could be in a census packet that arrives on VLAN 10 on leaf 1. VLAN 10 is mapped to VNID 10, and then that's sent across to the remote leaf, who's also in VNID 10. But that VNID 10 logically would map to VLAN 10, and then you have end-to-end packet transport. But that ingress VNID 10 could be mapped to VLAN 12, and you can essentially bridge those two VLANs together. So we have VLANs and we have VNIDs, and the VNIDs are what derive the kind of the transport and the connectivity model between these. Kind of similar, I guess, to how we can use MPLS as well. It's good stuff. What else? Oh, so there's not really a lot to say on VXLAN. It is a tunneling technology, and it's really good. BGP, everything is just rammed into BGP in the future, maybe a dystopian future. Because some dystopian's bad. Yeah. Euphoria. What's the right word? In the future, where things are all nice and simple, all you'll have is BGP. It will be BGP. It will be one protocol to rule them all. Yes. Anyway, did you ever? There's a BGP song. Google OPP BGP song. OPP, other people's packets, and the song is about BGP. It's amusing. We have new address families in the EVPN. So it's EVPN address family we use, and the MVPN address family if we're running multicast. What have we got here? So in here we've got route type 1. And this essentially is an Ethernet auto discovery route. It's used to advertise an Ethernet segment identifier. It's not supported in Catalyst. This is to support layer 2 dual-homed devices. So it acts as a switch, again, that's connected to 2 leaves. This is what this is used for. So we can do ECMP. So we don't actually support this. It's supported in Nexus with things like VPC, but it's just there for information. The route type 2, so this advertises endpoint reachability information. So this is the MAC and IP address, which is sent to the endpoints. So that's used for ARP suppression, for example. We talked about that one. So when a client sends an ARP request, the ingress leaf will say, oh, hey, I already know the MAC and IP because it was sent to me by the remote leaf. Here, I'll send an ARP reply on his behalf. What else do we have? We have route type 3s. That's the inclusive multicast route. So that's used for ingress and replication. So ingress replication, what that essentially is if you have a multicast packet, which is come ingress to a leaf, and it needs to be sent to multiple remote leaves, the ingress leaf will create a single packet per remote destination and send multiple copies. So if it's coming ingress on the leaf, the multicast packet, it needs to be sent to 3 other leaves. It will send 3 copies of that packet. So it's not really optimal use of your bandwidth, but that's kind of what it's used for. We don't have to do this, of course. We do have something called TRM, tenant routed multicast, and we'll get onto that in due course. Then there's the route type 4, and that's an Ethernet segment route, which basically this is used in conjunction with the route type 1. So basically what this does is this learns the downstream devices as well and creates type 4 BGP update. We learn with dual homed, and then we can basically elect to designate a forwarder for the downstream devices, and then only have one of the leaves sending packets towards the downstream rather than both. So in a layer 2 dual home setup, this allows us to keep on active standby kind of topology with a designated forwarder. Not supported in Catalyst, unfortunately. It's just there for interest. And then we have a route type 5, which is a prefix route. So this is just our IP prefixes that when we have a border, and we connect via EVPN, or we're redistributing subnets, connected subnets, then these create the route type 5s. All right, so that's kind of for the EVPN address families. And then finally we have 2 more, and then we'll close. So for BGP, IPv4, MVPN, so it's the multicast. We have 2 that are of particular interest. We have the route type 5. So when a multicast stream comes online, a source comes online and starts transmitting data, the BGP processor turn this into a route type 5 and advertise it to all its peers. Why did you do this? So that when a remote leaf receives a PIM join, they can have a look in the BGP table and go, oh, is there a source for this particular group? And if there is, we can go, oh, brilliant, that is really helpful. I would like to receive that multicast traffic. How do I express my intent to receive that traffic? Well, I'll tell you what I'll do. I'll send you a route type 7, which is a customer multicast join prune. Basically, it's a join. It's like, hey guy who sent me the route type 5, hey Mr. Leaf, please please send me that particular feed. I want to watch the football. It's topical. It's England. It's the World Cup at the moment. It's the World Cup. It's the Euros. So that kind of summarizes the introduction theory lesson on EVPN. We can look forward to the next lecture, which may be on underlay multicast BUM, broadcast unknown unicast traffic on multicast.
I don't have an answer for that.
Wow, I didn't even think I asked her anything. It was my Alexa. Stop. Or I might talk a little bit more about the different gateways. Actually, I might do this one next, the gateway types, because that's really interesting. So we will jump into the lab. If you're interested, let me know. I'll be interested to know your thoughts, your feelings. If you thought this was terrible, then tell me, and then I won't do any more. If you thought this was fantastic and you want to hear more of me rambling over lunchtime, this is quite a late lunch, then by all means, I am here for you. Have a nice day.